Well, hello everybody. Let me take us back to where we were in the last presentation. We have two equations here. The one at the top is one where the operator is the angular momentum operator squared, and it's operating on the wave function y. And again, since it's an operator equation, that same wave function y occurs on the right hand side, and we recognize that the eigenvalue is a constant and is a function of the wave of the quantum number j. This is equation 6.60 in your textbook. The second equation is Schrodinger equation, because we have the Hamiltonian operator here. And again, what we recognize is it's the same function, the same wave function in here, which is y. And we also find again that there is an eigenvalue, which is a constant. In this particular case, it's a function of 2 times the moment of inertia. So what this basically tells us is that spherical harmonics are also eigenfunctions of L hat squared. And the point here is that H, the Hamiltonian operator, and L squared, they commute. So this leads me on to the next part of the presentation, and this is section 6.8 in the textbook. And this basically says, and I'll write out the title of that section, the precise values of the 3 components of angular momentum cannot be measured simultaneously. And so why is this important? It's important because, again, it's going to influence what we learn about the hydrogen atom. The spherical harmonics that we've looked at so far are the angular wave functions of a hydrogen atom, as well as a rigid rotator. So we'll say they are the angular wave functions of a hydrogen atom. As well as rigid rotator. So we're also going to now make things a little bit more general, and I've mentioned this already, and we're basically going to say that L is angular momentum, and we're going to say that M is the Z component of that angular momentum. And so for a second, let's just go back and look at angular momentum for a second. So we're going to recall that Lx equals y times the linear momentum p sub z minus z times the linear momentum of p sub y. So let's just make sure we recognize that p sub z is the linear momentum in the z direction. And so we can write these down for all the momenta, right? So we can recognize how do we come up with operators. So let's suppose that we care about the operator for angular momentum L sub z. Well, how would we figure that out? Well, we would use the operator for linear momentum in the z direction minus z times the operator for linear momentum in the y direction. And we recall that we can go to our operator table, and we know that for example, the operator for momentum in the z direction is minus I h bar di by di z. So we can rewrite this expression here in the following way. And we'll go through and do that for all of the momenta. So L sub y, and this we're going to start to see is a little bit laborious. And in a second, what we're going to do is we're going to think about how we convert these equations to spherical coordinates. These are all fairly straightforward, all fairly easy in terms of our linear momentum. And you can go ahead and probably imagine, and you can figure out what I'm going to write as I write it. So we keep writing, oops. So those are straightforward, but again, it's tedious to convert these to spherical coordinates. So I'm going to do that for you. So we're just going to jump straight to these same operators in terms of spherical coordinates now. So L sub x is equal to minus I h bar, and inside the brackets is minus sine phi di by di theta minus cotangent theta cosine phi di by di phi. Okay. And this one is minus I h bar cosine phi di by di theta. And I would imagine that you'd be thinking to yourselves, oh boy, where are we going with this? Do we really have to work with these particular equations? And there's a reason why I leave the LZ angular momentum to the end, and that's because it is the easiest one of the lot. And that's it. So which one is the easier one? And if it didn't really matter, because it's somewhat arbitrary whether we pick an angular momentum in x, y, or z, Supposing we only had to pick one of those things, which one would you rather work with? And I think most people would say, this one here looks to be the easiest. And so that's what we're going to work with.